Hello, thanks, welcome. Can everyone hear me? Cool, to me it sounds like I'm just talking, it's great. I'll correct my name first, Donato Borrello. All right, and I want to give an extra shout out to everyone who came to learn about videos. That's pretty freaking cool. So this morning, I'm going to share some of my experiences with the nitty-gritty of adaptive video transmuxing. As specific as that might sound, it's actually a huge topic, but I promised you guys the nitty-gritty, and we're going to do it. All right, so what's the big idea with video transmuxing? You're taking video from one container format and moving it into a different container format. Today we're going to talk about MPEG-TS, which is a format that's only supported in iOS, and we're going to convert it to MP4, a format that's supported everywhere, particularly Chrome, which has about 44% of the market. Now for some context. What's going on with client-side video? Like this. A lot of people think video on the web is just take an MP4, put it in a video tag, and then add some CSS. It is for a lot of people. It's pretty cool for your blog or maybe a 10-second clip, but that's not what YouTube or Netflix or HBO or any of the big publishers are doing. Nowadays, adaptive bitrate streaming is table stakes for video players. Adaptive bitrate means that's the ability to change quality seamlessly from lower to higher when the bandwidth increases or the network is stable, and switch to lower qualities when the bandwidth is lower or the network isn't stable. All right, so client-side video. Here's the big picture. This one is so abstracted, it could be anything. There's a model of you and a controller, right? But I exaggerated the right-hand side, my left, for the purposes of this presentation. What we're going to be talking about is providers. And now you're asking, what's a provider? Oh yeah, I circled it. Nice. So what is a provider? Providers are an abstraction layer between the player and the type of media being played. If you're familiar with Node.js, you might be more comfortable with the phrase playback technology or tech. Having this abstraction is important because you want to be able to treat everything the exact same way. Whether you're playing that simple MP4 or you're playing something more complex like Dash or HLS, RTMP, or even Chromecast. Chromecast is a pretty neat example because the provider is actually not a video player, it's a poster image with an event router that talks to the Chromecast device. So within these, we're talking about HLS. HLS uses the MPEG-TS format that we talked about. And so now you're saying, like, why HLS? There's all these other options. Why are we talking about HLS today? Suffice to say, that's what most publishers are using, at least in our network. HLS stands for HTTP live streaming. It's a standard for streaming video created by Apple in 2009. It has a lot of problems, but maybe that means it has a lot of character. The next big one is going to be Dash, which we also support, and we're excited to work on that in the future. So, all right, we're looking into HLS. We're doing our research. I have a lot of really cool open source projects listed here. Some of them are actually HLS. Some of them are Dash. All of them use media source extensions or something related to HLS. I really suggest you guys check these out. I'm going to tweet out these slides, and I think there's some really cool stuff to check out. So you do your research, and then you decide, am I going to take it, or am I going to make it? Obviously, if we took it, I wouldn't be here giving the talk. So that's the punchline. But it's important to realize that you don't rebuild the wheel unless there's something you think you can improve on. We examined all the options closely, and we had to make a tactical decision. And that's where this slide comes in. Opportunities for improvement. Things that were good, but maybe we could do it better. The first one is time to first frame. This is a really important metric that we always focus on. And we came up with 3 strategies for improving it. The first one, and this is the most important one, is incremental transmuxing instead of batch transmuxing. I'm going to go into that shortly. The next one is jumpstart downloads. And next one's clever parsing using finite state machines. I guess there's no point reading it since we're about to go into it. The feature completeness, this is for like HLS v4, the multi-track audio. So this would let you switch from English audio to Spanish audio seamlessly without having to reload the video. And more streams supported. We have a frustratingly thorough test suite. So it's about 250 different streams, which are all broken in slightly different ways. And so we really wanted to make sure that all those were working. And so Caterpillar is born. This is the obligatory tech stack slide. Everyone has one. We use Webpack to bundle everything. Underscore we've been using for about 2 years now. There's nothing too crazy here, except that this is the first time we started using TypeScript at our company. And it turned out to be a really good solution for video transmuxing. And we also started using ECMAScript 6 with Babel to transpile it back in. And then the kind of interesting one is JS CSP, communicating sequential processes, which I'll get into shortly. And this is the architecture. This is obviously where the name Caterpillar came from. We tried to draw it in other ways, but we couldn't. It's a caterpillar. So the important part here is the blue guy on the bottom right, the demux plus transmuxer. This is where all the hard work of converting an MPEG TS to an MP4 comes into play. All right, so here's the first differentiator I talked about, incremental computation for transmuxing. The big idea here is that we don't want to transmux the entire TS file, which is going to be somewhere from 2 to 10 seconds worth of content, all at once before we start playing back. If we can do just 1 keyframe's worth of content and then start playing it back and then continue while the content's playing, continuing the transmuxing, you actually end up removing a lot of latency to startup time. What's interesting is that most keyframes, and this depends on your encoder, but they're somewhere between 500 milliseconds and 4 seconds apart. So that's the amount of time you could improve on. So in order to talk about how we do incremental computation, you kind of have to know what's happening, right? All right, MPEG TS file, this is what it looks like. It's a big binary file, and it's composed of a bunch of TS packets. Each TS packet is exactly 188 bytes. The first 4 bytes are headers, and no one really gives a shit. Can I swear? I just realized that. Some of the packets are special. The PAT stands for Program Association Table. It tells you where to find the PMT. The PMT is a program map table. It tells you how to split up the rest of the streams. We don't have to go into any of that. But the important thing to notice is that the TS packets are multiple different streams interleaved. Each stream is in order, but the interleaving isn't necessarily. It could be totally arbitrary. Groups of TS packets within the same elementary stream create something called a packetized elementary stream. And so groups of them create packets, right? So you've got TS packets begetting PES packets. For audio, you can just take the PES packets, just look at their payloads, and then start using it. But for video, there's an extra step called null parsing. We're going to get into that later when I talk about finite state machines. But the important thing to say is you get it, there's a lot going on. There's a lot of phases and steps. This represents all of the stages from the input, which is MPEG TS, to the output, which is H.264 video, audio, captions, and metadata. And you can see that by doing just enough work to get the first frame out, you don't necessarily need to do all of the parsing to get all of the TS packets, right? You could do maybe 20% of the work, and then by doing like a pull system, you end up getting a lot faster time to first frame. So creating that system, shown here, all of these arrows, right? How do we define the system and how do we send the messages? The first thought was event-based systems. Most of JW Player uses backbone events, or a twist on backbone events, and that seemed like the first idea. And then we kind of went into functionally reactive programming using streams. The first iteration of our transmuxer used RxJS with observable, and that was actually really cool. The problem was that with the default settings, what you're getting is push streams, and that's essentially batch processing. It means that as soon as the work is coming in, the work is being done and passed on to the next step. Those of you that know a lot about RxJS are probably thinking, well, why don't you just do back pressure using buffers? Well, you can. What it kind of felt like was it's starting to get heavier, and it's not really doing exactly what we want it to do. We're starting to have more trouble debugging. We're starting to have more trouble profiling, figuring out what's happening. I remember going through the debugger and seeing like trampoline, and I wasn't sure what that was. I realized I had to like understand a lot about the internals in order to understand like why certain pieces were slower than other pieces. And then while Googling around to learn about alternatives, I found communicating sequential processes. CSP is a way to define systems by specifying independent processes which interact through message passing. Shout out to the guinea pigs. The implementation of CSP that we chose is called JS CSP, and it operates on a primitive called a channel. And the important idea with CSP is that everything is either a process, which is independent and has its own state, or a channel. And the only way for two processes to communicate is by putting something onto a channel or by taking something off of a channel. And I always visualize that by like a little guy standing there, and all he can do is like pick something up here and like put it down over there. This is a really natural way to think about transmuxing. Looking back at this, you can imagine any one of these is an independent process, and every arrow is a channel. So we just found a direct mapping between our little diagram to our code, which is pretty awesome. Let's keep going. So when you use channels without a buffer, there's a secret benefit. With this model, a process is blocked as soon as it does its first unit of work. So what I'm talking about is, I'm one of those little nodes, I'm a process. I pick up a TS packet, and my job is to put down a PES packet. But if nobody is there to take the PES packet from me, so I put it on the channel, but there's no one taking from that channel, then I have to wait. And what's interesting about that is the whole system ends up getting like blocked until you request a frame. So when you start up the video player, you request the first keyframe, and that kicks off the beginning of all the processing. And it does just enough to get that keyframe, and then when you request the next keyframe, it does just enough for that one. And it does it bit by bit, only the amount of work you need. So that's like the big win with incremental transmuxing. The next big idea was jumpstart downloading. It gets dark with these slides, huh? So this is kind of a similar idea, but in a different form. So again, we need a little context. Your browser doesn't just get MPEG TS files. When you want to load a video, when you want to load a movie, what you're actually giving it is a master manifest. The master manifest has a list of media manifests, and the media manifest has a list of TS files. And these are all URLs, right? So the master manifest is just a text file, and so is the media manifest, whereas the MPEG TS is a binary file. The idea for jumpstart downloading was that sometimes you would find media manifests that were just huge. For example, we found a 10,793 line manifest. That's 248 kilobytes in file size, which at 1 megabit per second, that's 250 milliseconds of added latency until the download of just the media manifest completes, which means you haven't even downloaded the content to begin transmuxing. So what we want to do is, or I guess what you want to notice is, on line 7, you already know the TS file to download, right? And at 10,793, you know the TS file that you need about 2 hours later. So why do the complete download? Well, obviously you're going to do the complete download, but why wait for the download to complete? Why wait for all of the parsing to complete? Why wait for this text file to be converted to a media manifest representation model before you start the next download? Doesn't make sense. So you jumpstart it. As soon as you see the TS segment that you need, you start the download. And this is meant to kind of show, boop, what you get. We thought that this would actually have a much bigger impact than it did. Most manifest files aren't that shitty. I mean, bad. DVR streams tend to be the worst offenders. Live streams are almost never a problem. And VOD streams, you only really see improvement for the really long ones. This is kind of an example. One of our customers, Stars, has Captain America Winter Soldier. So I looked at it. 1,500 lines, 27 kilobytes. Not really a big win there, but still a win. One of the reasons for that is that when testing the Fetch API in Chrome 49, it turns out that even though you're getting streaming downloads, the chunk size is about 10 kilobytes, which for most things is like the whole manifest. So if you're getting it all in one chunk, there's no win. But for the bigger ones, you do get it. Okay. So the third differentiator. Nalu parsing with finite state machines. So first, I got to give you guys a quick refresher. We started with the MPEG TS file, then we had the TS packets. The TS packets became PES packets. And if that wasn't enough, one or more PES packets can beget one or more NAL units, or 0, if it's like an in-between one. And then NAL, which stands for Network Abstraction Layer, if I didn't say that already, creates groups of H.264 frames, which can then be muxed into video. And so this represented in this diagram is this little section. Now, I'm sure you're wondering, like, this is all really abstract. What does that look like? So yeah, the trick is with null parsing, you don't have a guaranteed idea of where they're going to start or end. The green arrows are evenly spaced. Those represent TS packets, like I said, 188 bytes each. The PES packets always start with a TS packet, but you know that a new one starts if there's a certain flag. It's the 10th bit of the header of the TS packet. With the null unit, you only know it starts if you see 001 or 0001 in the bytes, and that could be aligned to anywhere. So finding null units is a pain in the butt. They don't line up with anything. They can start and end anywhere. They can be any length. I've seen them as small as 2 bytes. And all we know is 001 or 0001. So how do you solve this? When doing our research, I saw a pretty cool solution by HLS.js, the Daily Motion one. They have a pretty killer optimization. They check every 3rd byte, and if it's a 0 or a 1, they mark it as a potential sync byte. And then they check around it to see if it actually is one. If it isn't, they continue. If it is, they actually realign and continue. That's pretty cool. It's kind of similar to what we're doing in our Flash one, but it's ultimately a lot of code, and it's a lot of conditional branching, which means it's hard to follow and it's prone to bugs. So we tried something else. It kind of seemed like we're pattern matching, right? Pattern matching is a pretty natural use case for finite automata. In this case, what we're looking for is 001 or 0001, and it's represented by this thing. So our code for the parser null is actually kind of interesting. There's about 80 lines which define the state transitions, and then there's about 15 lines which just run you through the state transitions, and then there's the logic which says, okay, at a sync byte, this is how I react. So it ended up, I think, being a lot cleaner code, and I actually didn't get a chance to performance compare them, but I got a feeling it's better. I think branch prediction on the CPU is going to be a little easier, but I better check that out. Cool. All right, so miscellanea. I wasn't sure how much time I'd have, so this is like the slides I could throw out if I had to, but I'm glad I have a chance to talk about. Adaptive switching. So we talked about transmuxing, but the talk is adaptive transmuxing. Adaptive switching is really challenging because once you start the second download, you actually have the rate of the original download, right? If you're downloading 2 segments at the same time. And there's a lot that goes into it. But the metrics that we care about the most that go into our algorithm are the time to download, the time to transmux. This is something that not many people are doing. I haven't seen it in any open source solution. Network volatility, this is another thing that we're doing that I haven't seen out there. Manifest accuracy, available qualities, and individual stream status. So network volatility, you can see that it's the safety factor. What happens is every time we see the bandwidth decrease, or we're in a state where the bandwidth was enough to support a level, but we had to go down to a lower quality level because the bandwidth decreased, we increase the safety factor. And what that means is that you're going to be a little bit more cautious when going back to a higher level. Manifest accuracy, that's a kind of interesting one. Sometimes a manifest will tell you, this TS file is about 2 seconds worth of content. Turns out it's 10 seconds worth of content. That means it's 5 times bigger file size, which means you actually anticipated that it would take a certain amount of time to download, and it took 5 times longer. So what we can do is fine-tune our estimations based off of how well the manifest is doing. The available qualities is obvious. If you have 240p, 360, 480, obviously switch to the correct one. An individual stream status. That one's kind of cool, too. If one of the media manifests starts 404ing, we're going to just we're going to leave it there, but we're not going to switch to it. We're going to move around it until it looks better. And this is the algorithm. Yeah, I don't really feel like reading it. Okay, I bet a lot of people here are really interested in the impact of using ES6. Generators screwed us. It was kind of a bummer because we're doing our profiling, and it turns out that V8 engine will bail if it sees generators. It's not even going to attempt to optimize things. The only solution that we ended up having was switching to regenerator using Babel, which converts it from generators back to like these big switch statements. So I think it made the code a little bit bigger, but brought us back to the faster browser optimizations. Another problem we ran into was that Uglify.js is only partially compatible with ES6. Again, regenerator helped us, but again, it's such a bigger file, it kind of sucks. And then Webpack plus Babel plus TypeScript was quite a hassle. TypeScript doesn't natively support a lot of ES6 features, so you have to enable it with like ES next option true. And in the end, it just took like hours to get it all working. And with that, I just want to say thanks to everyone.
Excellent. Come on over. Join me on this couch.
All right.
There's a beautiful butterfly on the stage, everyone, just in case you didn't. How are you? How's it going?
Pretty good. Yourself?
Lovely, lovely. How do you think your talk went?
I'm glad I cut out all those extra slides because I would have went way over.
I thought it was the best talk I've seen in the past half hour, so.
Wow.
High bar. Perfect. Okay, who are your top 2 open source personalities?
I love Adi Asmani.
Oh, good guy.
It's really cool to see people talking about tooling, which is one of my favorite things.
What was his recent tweet that you faved?
Ooh. I'm not that big on Twitter.
Okay, so not
I just
as
do
obsessed.
it for conferences.
Okay. Oh, gotcha. All right. All right. What is your least favorite open source project? Naming names.
I don't have one, sorry.
Such a positive person you are. Okay. What was your first thought when you woke up this morning?
I want to go back to sleep.
How did that work out for you?
I got another 15 minutes, so
good.
It was a win.
All right, all right. Okay, so we learned or relearned a lot of new acronyms today. What is your favorite?
My favorite?
SI. What does SI stand for right now?
Staten Island?
Is it?
Is it not?
Smithsonian Institute. Thank God we have Aiden up front. Saving the day. All right, so.
Did we get any tweets?
We don't have any tweets.
No
or
questions,
if we
guys?
do, here's the deal. The internet sucks, as conferences, conferences is what happens with conferences. Mm-hmm. Let's not make excuses, but I don't know. I don't know if there's questions. You're just going to have to deal with mine. What was your aha moment in programming when you were learning?
What jumps out to me as an aha moment was the first time I got a real program done in Scheme. Okay. It was like an n queens kind of question, and I was like, holy crap, it actually works. These weird functional programming works.
One fan. 2.
Well, we got 2, maybe 3.
What was the last thing you taught someone?
Did you learn nothing? Like.
Wow.
I'm sorry.
Yeah. Wait, what? Oh, they're good. Okay, good. Thank you so much. You may leave.